Hi, I'm Nicole D'Souza, bachelor student at the University of Alberta. Today I'll be talking about my episode, which is part of the webinar series for Tropi Dry. Today's topic would be on soil carbon flux of a tropical dry forest. Let us begin. The outline for today is 1. What is carbon flux and why is it important? 2. Where are we studying the flux rates? 3. How are we measuring the efflux rate? What are we doing with the raw data? How do we correlate the raw data to other variables to draw an in-depth understanding? Example data overview would be after that, followed by the conclusion. So, what is soil carbon flux? CO2 transfer, movement, or flux from the soil is a key element of soil respiration. Soil respiration involves root respiration, where the plant roots have tiny hairs that suck up oxygen. During this process, the oxygen is converted to carbon dioxide, which is diffused out of the roots by the same root hair. And the other would be heterotrophic respiration, and it's basically respiration due to bacteria in the soil, and the respiration rates of bacteria in the soil depend on their metabolism, which is also dependent upon temperature, humidity, and other factors such as wind and soil moisture. All of this directly affects the rate of nutrient release from soil organic matter, which is necessary in sustaining plant and other organism growth. So it's pretty important to study this. So the study site is Santa Rosa National Park in Guanacaste, Costa Rica. It's a tropical dry forest. You can see on the bottom right, it gets a lot of albedo and the forest is pretty dense. It's pretty close to the ocean, so it receives lots of humid winds. So how do we measure this carbon flux? We measure the carbon flux using 4 chambers in conjunction with the ACU, which is the LI8100 ACU, and it's connected to the LI8150 multiplexer. So if you look at the bottom right, you see the smaller yellow box is the ACU. It has an infrared gas analyzer, and it's connected to the bigger yellow box, which is the multiplexer. The ACU can be used with a single chamber, but if you want to use more than one chamber, you need the multiplexer because it's got a pump and different diversion systems for air. And we used the 104C long-term chamber, which is, you can see on the bottom left. It has a pivoting arm that swivels and closes over the soil collar. And typically we cage the instruments so wildlife don't damage it. And how does this work? It uses the rate of increase in carbon dioxide in a measurement chamber to estimate the rate at which carbon dioxide diffuses into free air outside the chamber. So for such an estimate to be valid, conditions must be similar inside and outside the chamber. These conditions include the concentration gradient driving diffusion, barometric pressure, temperature, and soil moisture. The CO2 gradient between the soil surface layer and air are not exactly the same inside and outside the chamber. This is because there is an increase in CO2 mole fraction inside the chamber. The diffusion rate is estimated and corrected for using an analytical technique explained later. This technique takes into account the effects of increasing chamber CO2 concentration on the diffusion gradient. So because of this, it's possible to estimate the initial rate of CO2 increase that occurs immediately after the chamber closes. These chambers have specially designed vents to prevent pressure gradients and wind incursions from the outside. And in a nutshell, it measures exponential increase in carbon dioxide over time, and it's a closed system. This is the formula that the LI8100 implements, and FC is the soil CO2 efflux rate in micromoles per meter squared per second. V is the volume in centimeter cubed. P naught is the initial pressure in kilopascals. W naught is the initial water vapor mole fraction in millimoles per mole. S is the soil surface area. T naught is the initial air temperature. The derivative of delta C prime over delta T is the initial rate of change in water corrected CO2 mole fraction in micromoles per mole. Some of the measurement parameters that are important for our observations, and the calculation is based on these. It changes for every survey, so this applies only to us. We use an observation length of 2 minutes, an observation cycle of 30 minutes. Deadband, which is time to allow for mixing of different gases, was 30 seconds. The distance from infrared gas analyzer to each chamber is 15 meters, which is the maximum length of tubing that we had. Soil area for the long-term chamber is 317 centimeters squared, and the extension tube volume is 237.0 centimeter cubed. On the bottom right, you can see what one of the deployed chambers look like. So, dealing with raw data, I'll play this video for y'all.
The LI8100A system includes exclusive software that allows you to quickly process large data sets and QA where a graph and recompute data very quickly. It utilizes an easy-to-read table so you can sort through key variables. This gives you the option to include or delete outlier data that may or may not be useful in your final analysis. You can view individual measurements, as well as graph and compare fluxes between multiple chambers. The LI8100A system simplifies processing and management of large data sets, saving you time and ensuring publication quality data.
So that's what we use to deal with raw data and to make our plots. So what can we do with this data? So the soil carbon flux data collected can be correlated to other parameters like pressure deficit, VPD, temperature, soil moisture, and precipitation. All of this can reveal valuable information about plant transpiration and soil respiration. All of this information provides a better understanding of forest health in an effort to prolong natural system life. So I'll go over one of the correlation methods, which is using the NVLink Mini WSN wireless sensor network. So we've got mini LXRS wireless nodes scattered throughout the national park, and these are 4-channel nodes that measure incoming and reflected power, which is photosynthetically active radiation, soil moisture, and relative humidity. The chambers are placed in close proximity to these nodes in an effort to get more data to correlate with. So the bottom left is what the node looks like. It's got 4 channels coming out of the face, and the power sensor is located on the top of the wooden stake, with soil moisture sensors going into the ground on the bottom, as well as the white radiation shield that shields the relative humidity sensor. The right picture is what the node looks like as a whole. So another method to correlate data would be to use phenological towers. Phenology towers can reveal valuable information pertaining to the impact of photosynthetically active radiation on flux rates in the footprint. Meteorological towers provide a basis for correlation of parameters such as wind, precipitation, and temperature to soil efflux rates. So these are both important to understand the different parameters that result in higher or lower flux rates. So the data overview for the rainy season is shown here. We've got flux, VPD, air temperature, and precipitation. It's to perform a correlation. MATLAB was used to find a correlation matrix, and the relationship can be seen in the next slide. I'll have this back for a different season as well, so like the data we had was correlated between two different seasons. Here's what the correlation matrix looks like. As you can see, VPD has negative correlation with flux. Air temperature has a slight positive correlation with flux, and precipitation has a slight positive correlation with flux. And basically, with low VPD, you would have high relative humidity. It responds by having a lower rate of transpiration, limiting the transport of minerals. And so the lower the transpiration, the less active the roots, which is why it's important to know how flux rates are affected by VPD. With more moisture and nutrients in the soil, flux could be at a high though. It doesn't matter about the vapor pressure deficit, because the soil respiration is directly dependent upon soil moisture instead. And air temperature has a positive relationship with flux because the warmer it is, the metabolism of the bacteria favors this warmth and can produce more carbon dioxide by respiration. Precipitation ultimately results in the soil moisture content being at a high. So that's why there's a positive relationship there. For the senescence or brown down season, we've got a similar chart: flux, VPD, air temperature, and precipitation. The correlation matrix is as follows here in the next slide as well. So now you'd have a higher positive increase in your VPD value, which is 0.16, as well as a steeper slope. With the massive VPD, dry air prevails, increasing transpiration, and your air temperature is at a higher value right now. And because of a higher air temperature, it results in a stronger relationship to flux, a stronger positive relationship to flux is what I should say, because as your air temperature is at a high, your metabolism favors the warmth and the respiration of carbon dioxide is at a high. The precipitation does not affect it as much during the senescence season, evident by the almost horizontal slope of the precipitation relation. So, in conclusion, understanding the soil carbon flux is an integral part of understanding the forest health dynamic. Correlating raw field observations to other environmental parameters provides a foundation to construct intricate response functions that allow us to comprehend what is happening within the forest. Thanks for watching my lecture. I hope you enjoyed it, and I hope it informed you about the cool chambers and the cool equipment that Lycor Biosciences has to aid in research, and have a great day. Thanks. Some references.